Hi, welcome to the ASB and ASA's Vic South Star Party and our live stream about the prospects for the Christmas comet. Hi, I'm Kathy.
I'm John.
And before we start, I'd like to say that in the spirit of reconciliation, the Astronomical Society of South Australia acknowledges the traditional custodians of country throughout Australia. We recognise them as the first astronomers on this land and their ongoing deep connections to land, sea and community. We pay our respects to their elders, past, present and emerging, and extend that respect to all Aboriginal and Torres Strait Islander peoples today.
Thank you, Kathy. And welcome, Michael. Hello, Michael. Good to see you here and all of the people out there watching. Hopefully there's a fair few watching. And that's who I'm talking to now because we've got a raffle. We have a big raffle going that's going to be drawn tonight at 9 p.m. Australian Eastern Standard Time, Melbourne time. So that'll be 8:30 here in Adelaide. We're broadcasting from Adelaide. Michael, whereabouts are you?
Swan Hill in country Victoria.
Swan Hill in Victoria. So we're a little bit apart there. More about the raffle very quickly. You can find out more about it on the ASB's homepage right at the start. There's a link and it takes you to all this text about the various prizes. Now, the first prize is a ultra compact equatorial tracking platform. I am reading this, so I apologise. I'm not looking straight at the camera. It's a massive prize there. It's got a polar scope with illuminator, Wi-Fi with selectable modes, free control app for Android and iOS phones. And it's got sidereal, solar and lunar tracking with automatic DSLR shutter release control. So if you want to stick your DSLR on there, there's a whole stack of stuff there. It's quite a sturdy one, so it takes about 1.5 kilograms or something. So you can read more about that. So it's quite a substantial amount there. Now, if you don't get first prize, second prize is pretty good. It's a very, very large 40-inch, they haven't gone metric yet, so it's a bit over a metre, telescope bag. So ultra durable, 900 denier. So it's pretty thick. It's huge. Looking there at the price, there's a whole lot of things there. You can put different internal walls in the bag and all sorts of things. It's valued at over $1,000, about $1,070, and it's going to be delivered by courier to your home, fully insured. So how's that? Now you'll be notified by email, but hopefully you're going to see it on tonight's show at 9 o'clock. So you can tune in on YouTube or Facebook for that.
And for this session, as you've already met, our presenter is Michael Mattiazzo. In 1986, Michael witnessed his first comet, Halley, which had him hooked on comets. Since then, he has made visual observations of over 245 comets, plus countless others imaged using a CCD camera. He joined the Astronomical Society of South Australia in 1990 and had the privilege to meet one of the greatest visual comet hunters of all time, Bill Bradfield. Discoverer of 18 comets, Bill was Michael's mentor and gave him much support in taking up comet hunting.
Very good. Now, Michael, we've all met Bill Bradfield, and Bill was a super nice guy, wasn't he? Can you hear me, Michael?
Yeah, mate, I can hear you. Yes.
Yes, we've both met Bill, a great guy, and he's passed away a few years ago now. The Astronomical Society of South Australia is lucky enough to have his comet hunting telescope there in our possession. So when you come over here, Michael, next, you can come and have a look at that. We're sort of doing it up at the moment, but I've got some more bio here that you've sent through, Michael. Although no longer hunting comets, Michael turned to searching for comets in the Swan data. Is that because you're in Swan Hill?
Me coincidence.
It is, is it? Okay. No, that's from the Soho satellite. Michael's got a tally of 9 swan comet discoveries to your name. 9. And of course, we already know that you live in Swan Hill. That's on the River Murray for those people watching overseas. The Murray River is the longest river in South Australia, and Swan Hill's sort of about halfway along from the mountains down to the ocean down here at Gorwin, where it comes out. You also submit astrometric data of comets to the Minor Planet Centre under observatory code Q38. What's Q38, Michael? Is that where your place is?
Yeah, exactly. Yeah, backyard.
In the backyard. So it sounds very technical, but it's just the backyard. So fantastic. So can you take us through all the stuff you do in your backyard now? Over to you, Michael.
Yeah, what I do in the backyard, basically, I use a C11 Reicherman Schmidt astrograph telescope. I actually don't even have an observatory. I just drag it out of the back, outside the house, and plonk it down, line her up to the southwestial pole, whack a Canon 6D camera on it, and 15 minutes later, away you go.
That's pretty quick.
Pretty much it. Yep.
Okay. Well, do you want to take us through? I guess you're going to take us through some of your discoveries. And so you've got the telescope outside. It's not raining, which is what I was doing last night over there, I think. What do you do?
So you're basically referring to the swan discoveries.
Yes. But what about your own telescope? Well, you can talk about both. Yeah.
Yeah. Well, with the swan discoveries, you pretty much. I spend about 5 minutes a day looking at the data from the Soho Swan website. So they basically provide their data in Comet Tracker map format. It's an ultraviolet camera in space. It's very low resolution, but it's very good at picking up comets because they shine brightly in the ultraviolet. So once I think I detect something in there, I'll then race out. If it's visible from my hemisphere, I'll race out and image the area where the object. You sort of know where it might be within a few degrees. So it's a very narrow sort of area of search. So it's a lot easier than spending hours upon hours of photographing the night sky and never find anything. So
a bit like Bill Bradfield did. He didn't have that.
Very much. So these discoveries in no way compare to the efforts that Bill Bradfield. He basically got up at 3 a.m, dragged his scope into the car, drove out kilometers to get to find some dark sky, and spend hours upon hours of visually hunting. So
he got 18, didn't he, Bill? 18
yes.
copies. Yes.
Yep.
That's amazing.
Yeah, but he done it in a time when he didn't have much competition, pretty much, or Southern Hemisphere based for a start.
Well, you weren't there.
True, but in today's day and age, the skies are literally covered by professional surveys. So the comets are discovered when very far from the sun now. So it's a much more difficult task to find a comet for an amateur, that is. So it's that's where that's where the challenge is at. So hence why I gave up visual hunting in favour of the swan, searching for swan comets in their data.
Do you feel, Michael, this is a bit of a loaded question, do you feel like you're sort of cheating a bit when you do it this way?
Well, it's not necessarily cheating, because it's you don't get your name attached to it. So none of my finds have got Machiarzzo on it. They basically got Swan. They're labelled as Comet Swan, which is where the prime detection occurred.
But you're a footnote.
I just get the discovery credit for it.
That's pretty good.
So, Mike, are you going to speak to us today about the Christmas comet? What's the scientific designation for that one? The C5. How does it go?
2021 A1 Leonard. Yep.
What's all that mean? So, can you take us through the nomenclature?
Yeah, I will. That's all part of my talk.
Okay, well, we'll be quiet. You take it away.
Yes.
No worries.
Okay.
So you're sharing the screen, seeing that?
Yep, we can see that.
Yep.
Okay. Yep. Cool.
See a green dot.
Pretty much. Just a green dot at the moment. Yeah.
Green dot.
So basically, this is an image of Comet Leonard that I've taken remotely a couple of days ago from New Mexico using an eye telescope. Now this is also a C11 raster, and it's about a 10-minute exposure using their T68. So it's currently only visible in the northern hemisphere, and it's still still a couple of months away from perihelion. So when this photo was taken, it was about 1.7 astronomical units from the Earth. And this distance will shrink very rapidly over the next 6 weeks. So yeah, so before I talk about Comet Leonard, I basically need to go to the basics and just explain what a comet is.
Actually, when you talk about 6 weeks, that's pretty scary. That Christmas is coming up pretty quick.
True story, very true story.
I just did the calculation then, and heck.
Yeah, yep. So you can see on screen here on the right hand side here we've got the Rosetta spacecraft. That basically orbited comet 67P Churyumov-Gerasimenko, which was discovered in 1969 by a couple of Russian astronomers. So yeah, the Rosetta spacecraft orbited this object for a couple of years, between 2014 and 2016, before settling down on the comet. So what is a comet? It's basically a small solar system body composed of ice, dust, and rocky particles. And the word comet originated in ancient Greek it meant long, hairy star. Now, the nucleus is typically 1 to 10 kilometers across, and it's also irregularly shaped, as you can see with 67P. Looks a bit like a duck. Like a duck.
A duck.
Yeah. So comets generally form beyond Jupiter, where it's quite cold and icy, as opposed to the asteroids, where the asteroids a bit more iron and stone. But you do get the transition objects as well, so you'll get asteroids that start showing cometary features. And another interesting object was 3200 Phaethon, which is an asteroid, but it's in a cometary orbit, but it's also the progenitor of the Geminid meteor shower that we see every December the 13th. So it's obviously been around enough times around the sun to be completely made inert, inactive, but it's still got loads of dust and rock in its orbit that always intersects the Earth. So it produces a very, very nice meteor shower. One other interesting feature about comets is that they're very dark as well. So if you can imagine yourself sitting on a comet, yeah, you might think you're looking at some snowy mountain-capped peaks, but unfortunately not. It's very pitch black. It's about as black as photocopier toner. Now, you may recall back in 1997 we had a great comet Hale-Bopp fly past.
Yes.
The larger comets of recent times. That nucleus was estimated around the 40 to 50K mark. And then recently, what's made a lot of attention lately is this new comet discovery, 2014 UN 271, Bernardinelli Bernstein, which is quite nice because it's got a human name to it, human element rather than a robotic robotic telescope element. This is the largest comet yet ever discovered, and they're estimating it to be around 100 to 200 kilometers across.
Wow.
And that's going to arrive at perihelion in 2031. Now, it might sound exciting, but unfortunately, it doesn't get any closer than Saturn. So I really think it's highly overrated. It's basically, it not only will it not become visible to the naked eye, it probably won't even be visible in a backyard telescope. Also interesting is the comets are quite low density as well. So there's an average of 0.6 grams per cubic centimeter. So a comet would actually float on water. So if you stuck 67P here on the ocean, say the Pacific Ocean, you get a duck floating on the water. So
okay.
there have been over like 4,500 100,000 known comets seen in since historical times. But it's actually a tiny fraction of what's actually out there, as opposed to the hundreds of thousands of asteroids that we've discovered since. Asteroids are all pretty much within the orbit of Jupiter, so a lot of them are in the Earth's vicinity. So when a comet approaches the sun, it develops a temporary atmosphere of pretty much water and dust. So this photo on the right here, you can see that 252p linear. I took this photo in March of 2016. That was a 3-degree field of view. The coma was over a degree across. It was quite large. It came very, very close to the Earth, one of the closest approaches of a comet to the Earth, and it was actually visible to the naked eye as well. So it was as appearing as a hairy star, actually. Surprise, surprise. Yeah. Now comas develop when the nucleus gets within 3 astronomical units of the sun. That's what they define as an ice line, where water ice will start to dissociate and evaporate off the nucleus. There is activity from carbon monoxide when much further away from the sun. So yeah, generally, and the size of a coma is typically 100,000, 200,000 kilometers across. So that's around the size of Jupiter, because Jupiter's around the 150,000 mark. But do note that the atmosphere is extremely tenuous. So you'd barely notice the coma if you're on the comet. Sometimes it can get bigger than the sun, which is about 1.4 million kilometers. Not sure if you remember that way back in 2007, late 2007, they had that big explosion of Comet 17P Holmes. That coma expanded out, blew out to a size bigger than the sun. Now also note that when a comet approaches the sun, the coma will also shrink due to the effect of the sun and become a bit more condensed. But comas are difficult to observe because you can see they're quite diffuse, so you need a dark sky to see it with much detail. Any sort of light pollution will make it a lot harder to pick out in the background. Now, the other great features of comets is that they can produce tails. Now, there are 3 types of tail. So the first tail here is the ion tail. Now, this was a photo of 2020 F8 Swan. So this was my discovery credit last year, showing a beautiful, well-developed ion tail. Now, these ion tails always point away from the sun, pretty much, because they're carried away by the solar wind. And they also develop when near the sun, and they can act as a windsock for a solar study. So when a comet gets smashed by a CME from the sun, it can swirl around quite a bit, and even disconnect from the head. They're difficult to observe because you're looking at fluorescent light, and it's blue light, which the eye isn't very capable of seeing in the darkness. But it's also very easy to photograph. And ion tails can reach millions and millions of kilometers. For example, in 1996, comet Hyakutake was detected by the Galileo spacecraft when it was about 500 million kilometers away. So, if you recall, Comet Hyakutake was an absolute cracker of a grey comet in March of 1996. So these tails can rapidly form and rapidly disappear. Now, a comet's dust tail is simply just dust escaping from the nucleus, because as you can imagine, the gravity of a comet is extremely weak. So it's very easy for dust to escape from the nucleus. And the dust is usually left behind in the comet's orbit, and often shows curvature. and it's affected by solar wind pressure as well. But it's easy to observe because it's reflecting sunlight. It can reach millions of kilometres, but not as long as an ion tail. And they're better developed post-perihelion. As you can see here on the right, this is a photo I took of Comet Neowise in August of last year. It became a very, very nice Northern Hemisphere object in July. We only saw the tail end of the show, pardon the pun. And they actually develop better when you have a comet with a small perihelion distance. Because the closer the comet is to the sun, the more it gets smashed by the solar heat, pretty much. And the third type of tail, which you don't tend to see very often, is the trail. Now, the dust trail is created by heavy particles leaving the comet, and they usually trail behind the orbit. And they are often seen more in Oort cloud comets, just from my experience. So I'll give you a couple of examples. This was 2014 Q1 Pan stars in July of 2015. They had showed a beautiful trail at right angles to the main tails. If you look carefully at that, you can see the thin bluish ion tail, and also the dust tail in that same area. But then at the 45, then at the 90-degree angle, you've got the trail trailing behind the comet. And then this is a picture of another Pan stars comet, 2011 L4, back in 2013. That clearly shows the three tails. You got the very, very narrow ion tail streaking pretty much up to the upper left about 11 o'clock. Then you've got the broader dust tail arcing, nice curvature there, and then you've got the that very narrow band of the dust trail shooting out to the left. So it was a beautiful comet, although that was a twilight comet. It's quite bright. It got to about second magnitude, but very low to the horizon. So the other question you've got to ask is where are comets from? So there are sort of four different areas where they can come from. Firstly, the short period comets. They usually have orbits of less than 200 years, and their orbits are elliptical. And you find this big population of Jupiter family comets. There's about 700 discovered so far. They've got orbits of less than 20 years. So you can imagine Jupiter being a giant vacuum cleaner in our solar system. Its gravity can trap comets, especially into resonances. So you've got a cluster of comets in a 6-year orbit, whereas Jupiter has a 12-year orbit around the sun. So it's a 2-to-1 resonance. And the bulk of the comets actually orbit in the same direction as the planets. So they're called direct orbits. And they're believed to originate from the Kuiper belt and migrate inwards via the outer planets. So the Kuiper belt's around the Pluto region, 30 to 50 AU. So this picture on the right-hand side, you can see where Voyager 1 is at the moment. It's around the 100 astronomical unit mark. And further out, you've got the Oort cloud, which is 1,000 to 100,000 times further away from the sun than the Earth is. And then for reference, you've got Alpha Centauri way out there, close to the million astronomical units. So the other, actually, I should mention that Comet Halley is defined as a short period comet with a 76-year orbit. But it's sort of against the grain. It does have a higher inclination and actually retrograde. So long period comets are defined as something as over 200 years, and they're thought to originate from the Oort cloud. They're also bound to the sun in an elliptical orbits, but they can come from anywhere. They have high orbit inclination, and often they're retrograde, meaning that their motion is reverse to what the planets are. Now, I've also put a point there that they're active at perihelion. So this is an important point because I'm predicting, well basically Comet Leonard will fits into this category of comet, as opposed to category, the Oort cloud comet, where they're estimating about 1 trillion objects, but they're obviously way too faint and way too small, way too far away to detect. And the Oort cloud comets are located in a spherical distribution. So, as I mentioned, 1,000 to 10,000 astronomical units away. And their orbits are parabolic as well, meaning that once they come in, you're only seeing them one time only. They're in and they're out. And generally, it's their first encounter with the sun ever. So they've never experienced heat at all. They've been stuck at minus 250, 70 degrees Celsius, which often, when they start to get anywhere near the sun, they start to show frosting. So they have this high activity when they're far away from the sun. So they give you that false impression that they're going to be very, very active when even near the sun. But they then fizzle. They fizzle out. They disappoint. And one of the classic examples was Comet Kohoutek in 1973. Was discovered when quite far from the sun. They predicted it was going to reach daylight visibility, and it even made the press as being the comet of the century, and it ended up being the fizzer of the century. Hardly anyone saw it. It became quite a faint naked eye object. It was a huge disappointment. So Oort cloud comets in general disappoint. So this is where Comet Leonard fits into that second category, not this third category, and I'll explain that later. And the final sort of region where the comets can come from are interstellar comets. And we only have 2 examples of this, 1I and 2I, and they've been discovered recently in the past 5 years or so. But as our detection methods become better and better, we will detect a lot more of them in the near future. So now moving on to our comet for the day, Comet 2021 A1 Leonard. There's the discoverer on the right-hand side, Gregory Leonard. He's a professional astronomer working at Mount Lemmon Observatory near Tucson, Arizona. I wish I had his job. He discovered this comet on the 3rd of January this year. Now, this was the first comet discovered in 2021, and it was discovered during the first fortnight of the year. That's where it gets the designation A1. So, any comets discovered in the second fortnight will get B. So B1, B2, B3. We are currently at T, I think. We're up to T. So I think we've had T1, T2, T3, T4. So it's quite straightforward.
Why did they decide on fortnights, Michael?
Well, basically, you've got 52 weeks, 26 fortnights, 26 fortnights, and it fits beautifully with the alphabet. So I don't think you can get. I don't think you get Z. I think Y is the last one in you. So it fits perfectly with the. So it makes quite sense. If you get a comet that's in a periodic orbit and it's detected on its second round in, it gets assigned a periodic number. So we're up to 450 something at the moment. I can't remember off the top of my head. So yeah. So even though I said so we had about 700 periodic comets, but there's 450 that are permanently labelled, and of course 1P Halley was the first ever periodic comet discovered.
Okay.
So yep. So tonight, if you're watching tonight's live feed, I should have comet 6P D'Arrest in view, and 19P Borelli. So look forward to this evening. Now, so basically, this comet was discovered when it was greater than 5 AU from the sun, so around the outside the orbit of Jupiter. And it was very faint at the time, magnitude 19, so beyond the reach of most telescopes. But, orbital calculations revealed that it would become much more interesting. So this comet's going to have a close encounter with the sun on the 3rd of January next year at 0.61 astronomical units, or 91 million kilometers. And that's inside the orbit of Venus. Even better, the comet is going to have a very favorable approach to the Earth on December the 12th at 0.23 astronomical units, or 35 million kilometers. Now, astronomically speaking, that's a pretty good approach, close approach to the Earth. And not only that, the orbital geometry of the Earth encounter will see the comet at a high phase angle, which could result in a brightness surge due to forward scattering of sunlight. I'll explain that in a minute. So a combination of these factors could set the stage for the brightest comet to appear in southern skies since 2011. Now, this was a photo I've taken of Comet Lovejoy in 2011, quite a long time ago. In my opinion, a great comet. I could visually observe the tail about 30 degrees with the naked eye, and even more with the binoculars. So just a bit more information about Comet Leonard. It's estimated to be a few kilometers across, probably 4 Ks approximately. It's also an all-cloud comet with an aphelion of approximately 3,200 astronomical units. That's enormous. It's a long period object. It appears to have been around the sun before, so 80,000 years ago. So if it's been around the sun before, this strengthens its survival prospects this time around, because it's been pre-baked. It's been stripped of all these volatile ices, and it's not showing this frosting. It's not appearing unusually bright at large distance from the sun, as the pristine all-cloud comets do, and usually fail once they get closer to the sun. So we're probably more likely to get a reliable light curve from this. So, and do note that after its encounter with the sun, it'll fling it out of the solar system altogether. So it's basically gone for good. So we do have JPL Horizon's 3D orbit tool, which I'll show you later on at the end of the talk. How bright will this comet get? So this is the fun part of comets, predicting its behavior. How bright will it actually get? But do note it is notoriously difficult, but there is a bit of science behind it. Now, the amateur comet observer like myself can contribute to the light curve, which we see at right here. So the red line is the Minor Planet Center predicted curve at discovery way back in January. So it's actually doing pretty well to what the prediction was back then. All these black dots are the measures. A lot of them are CCD measures as well, but they're mixed in with a bit of with a lot of visual recently. So the grey line that you see there is the sort of prediction for those visual observations. So you can see they're very, very close. And so that you can see that the Minor Planet Center predicted that the comet will peak at the 4th magnitude mark at closest approach in mid-December. However, it's not taking into account the forward scattering enhancement, which I'll describe in a minute. So it's not taking into account this green line. So if you look at the spike in the green line, we're going to predict that it's going to reach 1st magnitude. Now, also note the stable light curve. It's not deviating from it. So it adds adds extra confidence to the prediction. So what is forward
Michael,
scattering?
just to interrupt with a question we've got online, sorry, before we move on too
Yeah.
far. How do we know that it's been around the sun 80,000 years ago? Is this orbital calculations and simulations? Is that how we make these assumptions?
Yes, basically calculated. Yep. We've had 9-10 months of astrometric data.
I see.
So, and we basically.
So they position a track for a period of time and then sort of extrapolate backwards?
Yep, that's exactly right.
Who does that, Michael?
Minor Planet Center and the Jet Propulsion Laboratory. There's two different sites.
They come up with the same answer, hopefully.
Yep.
That's good.
Yeah, pretty much. Yeah, exactly. They're the two. There's probably more sites, but they're probably the two main ones I would use to look at orbital calculations.
We acknowledge a few other questions too. We'll get to those in a minute, but that one was relevant.
To get really quickly.
Of course, yeah, definitely.
Move on.
Thank you. Yep. Sangulum, thank you.
Right, so forward scatter. Okay, have you ever seen an airplane contrail at sunset or sunrise? And the closer the airplane is to the horizon, the more spectacular it appears. In fact, I've heard of lots of people think they've discovered comets at sunrise or sunset because the contrails are bright and spectacular. So the same feature applies with comets. At small scattering angles, micron-sized comet dust particles can scatter sunlight hundreds to thousands of times more strongly than at a side angle. The larger the angle, up to a maximum of 180, which is where you're actually staring at the sun, the more in line the comet is with the sun. And the other very interesting thing is it's a log scale. You will see exponential rise in brightness. But that, of course, is offset by its proximity to the sun. Now, Comet Leonard, the phase angle will be greater than 120 degrees between December 9 to 22, reaching a peak of 160 degrees on December 14. So just remember that date, December 14. So I'll give you some predictions. Now, many of you recall the Great Comet of McNaught, Great Comet of 2007, which sort of surprised everyone. It ended up being visible in daylight in about minus 5. Not that I'm saying that Leonard will, but I'm just saying that this comet was visible in the daytime. But the predictions there didn't consider the forward scattering effect. There is a paper regarding that, so I've got that there for anyone that's interested. Now, with this paper, the magnitude gain observed with McNaught, so you get a 1 order of magnitude gain when the phase angle hits 130 degrees. So Leonard will reach this on December the 10th. So we can predict possibly that the comet will be 3rd magnitude by then, and then a 2 mag gain at 145. So Leonard reaches this on December 12 and 17. So it could be 2nd magnitude by then. So just having a coffee. Now at 149 degrees, that's where Comet McNaught reached its maximum phase angle, and that raised it by minus 2.3. Now Leonard is going to go a step better. On December the 14th, it's going to have a maximum phase angle of 160. So technically, you can get 3.5 to 4 mag gain just based on that alone. Now, obviously, this is dependent on the dust production of the comet. Now, it's also a pre-perihelion encounter, so it's not. It hasn't been past the sun yet, so it's on its way in still. So the effect may be less pronounced. And it also assumes a baseline peak magnitude of 4th mag. Now, we don't. Now, the baseline peak could actually become brighter than fourth mag, or fainter. But we're going to get a better idea of that in the next month. So ask me the same question a month later. Now, also it assumes the comet doesn't fizzle out. So comets are unpredictable; they can do whatever they want. And obviously, it's not very effective with gassy comets because it doesn't work. So this is a photo I've taken remotely of Comet Leonard on the 26th of October. Now, that's got a very bright nucleus and it's got a very dusty tail. So that tail there is about 6 arc minutes. So it is already showing significant dust tail development. So that's a very good sign for the forward scatter brightness surge predicted in mid-December. And just want to mention something else. This comet will cross the orbit of Venus on December the 17th. It actually intersects the orbit of Venus. And this will occur less than 3 days prior to Venus actually being there in space. So basically it's missed Venus by 4 million kilometers, so Venus is probably going to get pelted by meteoroids from the dust trail a couple of days later.
Will any of that be visible, Michael? Will we see them in the sky together?
Oh yes, yep. So basically,
remember, sorry, Michael. Remember, sort of a shoemaker levy where we can see little holes punched in Venus's atmosphere. I mean, it's probably not going to be like that, but is that possible?
Not
question
likely.
Without notice.
No, not likely. No. But in my lifetime, I have seen a comet impact Jupiter in 1994. I've seen a near miss with Mars in 2014 with the comet sighting spring. And this December, we're going to see a near miss with Venus. So it's merely a matter of time. It's merely a matter of time before one's going to get exceptionally close to the Earth. And you basically have that 1 year notice.
Yeah, so really it's not, I mean, it's really obvious that we've been pelted heaps of, hundreds of thousands of times if all this happened a mere 20 or 30 years or so, even less.
Yeah. Yep. We do get the Leonard meteor storms every 33 years or so. But the primary body, the comet Tempel-Tuttle, won't collide with the Earth in the near future. Anyway, not now.
You saw that, Michael. I know there's a few other Astronomical Society, South Australia people, a whole group of us went across there to Sunset Country in Victoria, where you are, rented the little hut there in the Sunset National Park, and there's a whole stack of it. And I could not believe we were going to get up about 3 a.m, but I think Fraser, who's on at the quiz a bit later on this afternoon, was tooting his car horn, and we all sort of woke up in our tents or swags. Come outside now, come outside. And I went out, and this thing went across the sky and just lit up the whole area, and I could not believe it. And after that, it was just literally dozens per minute almost. It was the most incredible thing I've ever seen.
I gave up counting a bit after 2000. Yeah, it was phenomenal. It was phenomenal. But Venus will get absolutely smashed, I can assure you. But we won't be able to see that though, not unless they've got a satellite in space. But I think it's a Japanese satellite around Venus at the moment. But anyway, just finally, the viewing prospects. So basically, it's restricted to the northern hemisphere for pretty much all the way through to mid-December. So just for our benefit of our northern hemisphere viewers, I've thrown in a chart from the UK from the December the 1st to the 12th. It'll be morning sky before dawn, and you'll see it. So basically from the start of December at magnitude 6.5, and brighten very, very quickly to 4 or even possibly 3rd mag by December 12. You can see a very interesting encounter with Messier 3, the globular cluster, on the 3rd of December. I've already booked my eye telescope time for that. And then something else very, very interesting is going to occur on December the 8th. It will, the Earth will cross the orbital plane of the comet. So what effect that has is, and only the Northern Hemisphere people will see it, you will see the dust tail edge on, much like an edge-on galaxy. So it will appear as a needle, narrow spike, which might even be pointing in the solar direction as well. So you get what's called an anti-tail. So that'll be a very interesting feature, and that feature will be seen probably a day or two either side of that crossing. So that's one thing to keep an eye out. So I've booked my telescope time for that as well. Now it does go bad for the Northerners from say the 10th, 11th. It moves into the evening sky, and you can see it basically hugging the horizon. So it's going to be very low to the horizon in twilight, going through Ophiuchus and Sagittarius. So on the 12th, it'll be at its closest point to the Earth at 0.23, and so we're basically potentially looking at a second or first magnitude comet with a very, very bright dust tail. And then just note, if any iron tail, I'm sure there's definitely going to be an iron tail with it as well. That'll be sticking up perpendicular to the horizon. So, and that could reach, 10 degrees or more. So even though you think it's low, I'd still make attempts to photograph the iron tail sticking up over the horizon when the sky gets a bit darker. Now for the fun part, the southern hemisphere, we get a fantastic view of it, all the way into perihelion. So our first view this chart is 35 south latitude. It's also evening sky, and so you probably look around the 10 o'clock mark, 10 p.m. at night. It'll be very low to the horizon initially, but you can see that the visibility will rapidly improve each night. So from the 16th, put your diaries down from the 16th of December, as the comet goes through Sagittarius through to Microscopium. So, and I'll sort of predict that the magnitude will possibly be around magnitude 2 with the forward scatter surge, and then fade to mag 4 by the end of December. So because due to the effect of the comet moving away from the Earth, as well as the phase effect becoming less and less.
Yeah. Matty, I've got a question. Sorry, yes. I just interrupt there. Got a couple of questions. We've got a few highs there from Paul up at Mount Bryan, which is a good walk if you're fit. Chris Wyatt asked a question: do we usually see anti-tails on comets pre-perihelion? So anti-tails on comets before they reach the sun, before perihelion.
Well, obviously a tail / anti-tail. Well, anti-tails can only occur with dust if you've got dust in the comet. It's merely a perspective effect, so it just depends on which way the tail direction is going. So you can. So yeah, hopefully that answers the question. But yeah, obviously post-perihelion comets have their tails have a lot more dust released as opposed to a pre-perihelion. So it may not be as pronounced as, say, Comet R and Roland in 1957. That was a post-perihelion encounter. The dust was far more pronounced then. So hopefully
that's
that
a bit before my time.
Yeah,
long way before Kathy's time.
Yeah, take a look at just do a search, do a Google search, Comet R and Roland, and have a look at some of the photos.
I'm sure we've got some ASV members that can remember that.
Yep. So just about finishing off here. Basically, so the other great news is that the full moon will disappear. So from December 21, we should be able to see this comet in a dark sky, well away from the sun, reasonably well developed. So it should hopefully, fingers crossed, be the best comet seen in the past 10 years for the southern hemisphere. The northerners got Neowise last year. That was quite impressive, but we missed out on the big show of that. Just one other thing to note: comets are unpredictable. They can explode and break up. So anything's possible with this. So pretty much the conclusion of this all is, I'll put a quote there from David Levy. He was a famous comet hunter. He says, comets are like cats. They have tails and do precisely what they want. But I say comets, like cats, are predictable to a certain extent. I've got a couple of, if you want to keep up to date, I've got the Facebook page there. You don't need to be a Facebook member. You can just click on it and have a look. So I'll be posting regular updates and seeing whether this thing sticks to its prediction or whether it gets better than prediction or worse.
That's a beautiful shot there. I bet you that was taken down Henley Beach or somewhere.
Henley Beach, well done. Good job, well done.
Yeah. You know what? I reckon I think we've all got that shot. And I think there's one of our ex-members, bless his soul, Steve Cook, under that.
Absolutely.
Just after he had a swim, I think he got out of the water. So now we have another question there, Kathy.
Yeah, from Mark. He asked a bit earlier, but because we've got a few minutes left, I thought we'd try this one. He missed Hayakataki. He's just wondering if you could share your memories of that one.
Oh, he missed Hayakataki. Right. Wow. Well, guess what? I pretty much missed it as well. I only had one decent night, pretty much. And I was very, very upset too. So it basically, the reason it became a great comet was that it approached the Earth to 0.1 astronomical unit, which is very, very close, astronomically speaking. And at the time, it underwent an outburst as well, which was absolutely brilliant. And it, but the only problem was it moved north very, very quickly. So the 23rd of March was probably the best night for Southerners to view it. And I missed out on that night. Because I had a wedding to go to. But never mind. It's a Saturday night. What do you expect? But I did see it on the Friday night, and I saw about 20 degrees of iron tail. But basically, the following night, that tail had grown to 50 degrees, and then 100 degrees, then 100 degrees the day after that. So it was, as I said, with iron tails can rapidly grow and rapidly disappear. So there's all potential for Comet Leonard to develop a similar length of iron tail. No. I don't want to I don't want to put my foot in it and say we're going to see a massive iron tail, but anything's possible. If you don't look, you'll never know. So the whole basic principle of all this is to actually go out every possible night that you can to look at this thing, because it's going to change very quickly. It will appear very different every night. So that's one of the most fun things about comets.
I remember Bill Bradfield making a comment to me once many years ago about comets or finding comets. He said to me, "John, you won't find a comet watching TV." He actually said that. So
yeah, exactly.
That's I remember him saying that. Yeah. Anyway, I think we're just about wrap up there. We've got
lots of thanks online. Great talk, fantastic talk. So thanks very much, Michael, for sharing that. I'd like to remind everybody to get wrap up
9 o'clock tonight, and you can just go to the ASV homepage, click on the links, and buy your tickets there. So we've got a few hours left, and we'll keep plugging them for the next show. So we'll see you back here in roughly an hour, I think, with the quiz. So you've got an hour to study up and
Be ready
check the latest quiz quiz questions online, Google it, whatever you have to do. And we'll be here waiting for you in about an hour's time.
So on behalf of the Astronomical Societies of both Victoria and South Australia, thanks for joining us for this stream, and we'll see you soon for the quiz.
See you later.
Bye.
See you, Matty.
Yeah.
Mr. X.
Mr. XX.
That's right.